Okay, let's take a look at, it's a very short workbook chapter. Let's take a look at these alcohol synthesis problems. Wasn't a huge fan of the last workbook synthesis problems, but I think they were informative from a learning perspective, but a little bit too open-ended. Let's see. So yeah, so in this first problem, they're giving you an alkene, and they're asking you to convert it over into this other molecule. Let's take a look here. So the thing that stands out to me here is you're joining two molecules together. Okay, I like this problem. You're joining two molecules together. So you've got this carbon that is inside of the cyclohexane ring. And then you've got another two other carbons outside. So 1, 2, 3 there. And so 1, 2, 3. And then from the other side, we could see that you could take another one of these. I'm going to call that 4, 5. Actually, it makes more sense to call it carbon 4, 5, and 6. So you can see that you're going to somehow have to bring two of these materials, two of the things you're given to start with together. And so the obvious place to break this, to me, so the first step is to kind of look back and try and figure out how to break it up into smaller fragments. The obvious place to break it, to me, is right here. And so typically when you're looking at carbon-carbon bond forming reactions, we only have that alkyne reaction to work with. But you'll note that this is not a carbon-carbon bond that's formed to join these two things together. It's an oxygen bound to a carbon. So carbon 3 is not directly bonded to carbon 4. It's carbon 3 is bonded to an oxygen, which is bonded to 4. So we know a couple of ways to make oxygen carbon bonds. How could we do that? So I would say where to start is like form an oxygen carbon bond. How do we do that? The thing that stands out in my mind in terms of this is, just a simple reaction. Let me do a little bit more fancy. This reaction. If I've got this and I react it with an alkyl halide, for example, I can do some SN2 chemistry. And this is sort of the power of knowing those SN2 mechanisms and such. As I can join these together. So this isn't like a reaction I know from a flashcard. This is just a reaction that I can kind of come up with independently. And we'll name this reaction when we get to the chapter on ethers. But okay, so that's a way to do it. You can use some SN2 chemistry to form an oxygen carbon bond. All right, so let's go back then into our problem, and we're going to get rid of this. So this is just tying it back to, I don't know, something you can kind of wrap your head around. But let's take a look then at our molecule. So I guess I'll leave these. So what I would say is just break it here at the oxygen carbon bond into a nucleophile and an electrophile. So I know that if I do this reaction in the forward, so this is me thinking in reverse here, but I know if I do this reaction in the forward, what I'll get is that will go there and kick that off and give me this molecule. That's my thinking. I can use some SN2 chemistry to get at that bond. Okay, so now that I've broken it into smaller fragments, I need to figure out how to make those different fragments. And Now the problem becomes, I don't know, a little bit simpler, I think. So I start working in the forward direction. I've got an alkene. Let's look at this first. Let's look at the alkyl halide first. So I want to make this, let's say I want to make this first. So that one we kind of know already. We know a lot of different ways to make alkyl halide, and we know a lot of reactions for alkenes. This one we can actually do in a single step and just add in HBr and peroxides, and that gets us, oops, Br out. So that's it. That's that part. Not an issue at all. All right, what about this other part though with the carboxylate? So when you have a carboxylic acid and you deprotonate it or whatever, we call that a carboxylate. How could we make that? So we're starting with an alkene. I guess what I would start out if I was in your position, oops, not being super familiar with this stuff, I would just start out thinking, what are the different ways I know how to make a carboxylic acid? Right, so how do I make a carboxylic acid? The most obvious way, so one is you can do ozonolysis on an alkyne. That, you can look at that, but that's going to be a much harder route to push because you're going to have to break a carbon-carbon bond, which we're not doing here. The more obvious way to make a carboxylic acid is the way that we just learned, which is to take a primary alcohol and oxidize it with chromic acid to a carboxylic acid. Carboxylic acid can be made into carboxylate by just using, sodium hydride or something. I'll get back to that. Let's just start with this part. Okay, so I just want to make this into a primary alcohol then, which I know how to do. That's some of the very first chemistry we learned, is I will take BH3 and work it up with sodium hydroxide and peroxide, and that gives me a primary alcohol. Of course, I don't want the primary alcohol. I ultimately want to get to a carboxylate, so now I take that and I subject it to chromic acid. This ties it nicely back into we've already learned about in the last chapter. Okay, so now I end up with this, right? And then I just want to make this into the carboxylate, and so a solid strategy for doing that is, this is just acid-base chemistry, but we can use the same strategy we used for making alkoxides, where we just take a base, specifically sodium hydride. So you could use sodium if you use, like on an exam. Again, not that I'm giving you written exams, but if you were to use like sodium hydroxide, I'm sure we'd give you credit for that. But this will give you the carboxylate out. And now in our last step, we can just take, so that's, now we've taken this, and we've successfully made that in a bunch of steps. And now in our final step, we just combine those two molecules. We take this, which I'm just going to leave the sodium off altogether, and I can combine it with this, and then I get my product that I'm trying to ultimately push towards. Which is this. So a problem that looks, pretty intimidating on first glance, once you figure out the key step for it, which is that you have to break it right there, it becomes not as hard. Because then you're just going through synthesizing the fragments. And if you're just kind of getting, well, at this point, hopefully you're a little bit farther along than just kind of getting your feet wet with synthesis. These are more challenging problems probably than what are written in the textbook, but they're what you're actually trying to get towards. Okay, this next synthesis problem, we're starting with cyclooctane. is an interesting one. We're wondering, how can we take that to this open chain carboxylic acid? Note that this thing also has 8 carbons. The ring has 8 carbons as well. And so all we're trying to do here is break one of these carbon-carbon bonds. And all the carbon-carbon bonds here are equivalent, so I'm just going to pick one and say we want to break that one. Or let's say we want to break 1, 2. Let's say 1, 8, because that makes more sense with the way I've numbered them there. Okay. All right, so yeah, so how are we going to do this? Well, part of the problem is already solved for us because we know that if we're starting out with an alkane, regardless of how weird it looks, because we've never really worked with a cyclohexene, all we have to do is add in some light and some molecular bromine. And now I have brominated at least one position on that ring. And I want to push this towards a carboxylic acid. So there's a couple of ways you could do this. I think the safest way is probably to use LDA. That gives you an alkene. And then you could cleave that using ozonolysis. So again, I know to use ozonolysis here because I know a carbon-carbon bond is breaking, and that's the only way I know how to break carbon-carbon bonds. And that will give me 1, 2, 3, 4, 5, 6, 7, 8. The aldehyde. And then I could oxidize this up with chromic acid, and that will give me my product. So when we looked at chromic acid, we looked at it for oxidizing an alcohol all the way to a carboxylic acid. Naturally, if you start out with something that's more oxidized, like an aldehyde, you can, if you look at that lecture, it'll make sense. You can go to the carboxylic acid. The other way you could try and get through this problem, which I think would also work, this might be what the workbook wants you to do, would be to take use Br2 here. I apologize about my octagon drawings, they're not great. Okay, so now I've got Br2, and then you could use, this would be tough to do, I think, but if you use an LDA in an excess, you might be able to put an alkyne inside of here. You're going to get a lot of strain inside of this thing. Three, 4, 5. Oof, it's a tough one to draw. 8, 6. Looks something like that. 1, 2, 3, 4, 5, 6, 7. Oh, I picked up an extra carbon. 7. I feel like I need to take like an advanced art class to be able to teach this. All right. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there we go. Okay, yeah, you can see these are not that common. So having an alkyne in a ring, so you could do ozonolysis on this. and that will give you the carboxylic acid, so that works as well. The only issue you have with this, I'd say, this strategy, is that forming alkynes in rings is hard. And the reason is that this bond angle here should be 180, but you're inside of a ring, so you know, the ring constrains that. You can't be 180 and be inside of a ring. So I think cyclooctane is the smallest ring that you can even get an alkyne in, which is why I think they chose that for this, so that the strategy would work. If you have like a cyclohexane, there's no way to get an alkyne inside of that. So I would stick to the other one. Like if I was trying this in the lab, I would probably start with the other one where you do the chromic acid oxidation of the aldehyde. It just seems easier. I imagine getting the alkyne in there is tough, but either one of these is fine. So that's how you would work those two problems. Let's see. I'm trying to think of other things to talk about with alcohols and synthesis. Yeah. This is the workbook problems. I think that's probably good. I think the only thing other thing I would say. No, I think this is a good place to stop. So yeah, so that's how you solve those two. I'll do some mechanism problems in the next video.